Hey, Honors Pre-Calc. Today we are officially starting lesson 7.1. That means we're starting unit 7. We're leaving trig functions behind, at least for now. And we're going to take a look at our unit on probability, sequences, and series. So 7.1 is officially titled Sequences and Series. And our essential question for this lesson is, how do you represent the terms of sequences and series in multiple ways? Here's what we're going to do. We're going to represent the terms of a sequence explicitly and recursively. You'll see what that means. You will learn about the Fibonacci sequence, and it's a common infinite sequence. Some of you might already know what that is. And you'll understand how to write an infinite and a finite series in sigma notation. You should already know just basically like there are these things that exist called sequences of numbers that have a common pattern between the terms. Like you could add a certain number every time or divide by a certain number every time. We're going to kind of review that. And as you can tell, we're going to be talking about infinity a bit. So you should have just a general sense of what infinity is, which I'm sure you do. Something you'll be able to do by the end of this lesson is find the first 5 terms of the sequence. A sub n equals and this fraction. All right, so that's the kind of thing we're going to be looking at today. Got a lot of like vocabulary that just goes into sequences and series that's going to be important. So I'm going to switch over to the notes so we can get started. All right, here we go. So we've got our 7.1 note sequences and series. There's a whole bunch of vocab here. We're only going to talk about the first term initially. So let's take a look. A sequence, an infinite sequence is a function whose domain is the set of positive integers. Remember, domain usually means like the x values of a function. So if you're thinking about this on a graph, we're only going to be looking at every whole number on the positive side of the x-axis. And that's the only spots where we exist. So it's going to be like a bunch of dots, one every number. And it's all about where are the y values. So what are the terms for every dot, right? So when, we refer to them as n. So it's like when n is 1, what is this term? When n is 2, what is this term? When n is 3, what is this term? This really just means a series of numbers instead of like a smooth curve or line that we usually graph. Okay. The function values a sub 1, a sub 2, a sub 3, a sub 4, etc. are the terms of the sequence. If the domain of the function consists of the first n positive integers only, the sequence is a finite sequence. So we have this difference between finite and infinite sequence. If there's only, say, 4 terms, then 4 obviously is not infinity, so we would call that a finite sequence. But if the terms go on forever, then we call it an infinite sequence. And we're going to come back to all of the rest of these vocab terms, but let's just take a look at example 1. Writing the terms of a sequence. Write the first 4 terms of the sequence given by each of these. So in letter A here, you see it says a sub n. We're going to write the first 4 terms. It means we're going to write out when n is 1, when n is 2, n is 3, and n is 4. So I could even list that out to start. Okay, and all I'm going to do is plug in that sub number for n. Shouldn't be too bad. So I do 3 times 1 minus 2, 3 times 2 minus 2, 3 times 3 minus 2, and 3 times 4 minus 2. And so I'm going to go 1, 4, 7, and 10. And if you just look at the answers, you should be able to tell that the common occurrence between each term is that we're adding 3, right? And you can tell that by the 3n. We'll dig a little deeper into that later, but this is a pretty simple sequence. The terms are 1, 4, 7, 10, and that represents the first 4 terms. This is different than a normal function, as I was saying, because it's not like if we graph this, we would have some sort of a curve. We would literally just have dots. And you know what? Just to help you visualize that, let's actually do it for this one. So if I If this is like my x-axis, which is representing my n's, I might even label it with an n. And I only have 4 terms, so it's going to go 1, 2, 3, 4. And on the y-axis, I have to go at least up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like that. And when n is 1, the term is a 1. At 2, we're up at 4. At 3, we're at 7. And at 4, we're at 10. So that's what a sequence looks like visually. It's literally just dots on a graph instead of a curve or a line. Nothing connected, just a bunch of dots. However, it would be pretty common to just see it as a series of numbers, as a sequence of numbers instead of looking at it on a graph. But let's look at letter B. A sub n equals 3 plus parentheses -1 to the n. All right, let's see what happens this time. Again, we're finding the first 4 terms. So I'm just going to plug in each corresponding n value for n. And you can see what's going to happen here. Now, putting -1 to a power is a pretty common occurrence in a sequence. And what it does is it makes the sign of the 1 alternate for every increase in the number n, right? So -1 to the first power is just -1. -1 to the second power, -1 times -1, it's going to be a double negative. So it's going to become 3 plus 1. -1 to the third power stays negative because it's an odd power. And to the fourth power, it becomes positive again. So it alternates every time. And that means that the terms in this sequence are going to start repeating. So we have 2, and then a 4, and then a 2, and then a 4. And if we kept going, that pattern would continue. It would just go 2, 4, 2, 4, 2, 4. And if we graph that, it would go 2, 4, 2, 4, 2, 4, 2, 4. So that's what's going on with that one. All right, so there you go. There's the first 2 questions. We are going to keep going with example 2. Right, the first 5 terms of the sequence given by a sub n equals -1 to the n over 2n plus 1. Notice that this example is called a sequence whose terms alternate in sign. So now you're going to see how the -1 to the n can be used to alternate sign, meaning it goes positive, negative, which hopefully makes sense if you think about what we were just saying, that if this is an even exponent, the -1 is going to become positive. And if it's an odd exponent, it's going to stay negative. So let's see what happens here. We're going to find the first 5 terms. So we're doing A1, A sub 2, A sub 3, A sub 4, and A sub 5. All right, so let's try it. This time there's 2 different places where n is. So I just plug the same number in for both. Okay, and so in A sub 1, -1 to the first gives us a -1. 2 times 1 plus 1 gives us a 3. And the second one, -1 squared, is +1 over 5. Then we have -1 over 7, +1 over 9, -1 over 11. So there's the first 5 terms. You can see if we were trying to determine the pattern here in the denominator, we're increasing by 2 every time. And in the numerator, we're just switching between +1 and -1. Okay, so our next task in example 3 is going to be to actually take a pattern or a sequence and come up with the apparent nth term. So it's kind of like working backwards. We're going to try to find this notation for the sequence. And we're going to use some of the skills that we already saw. So if there's an increase in a certain number every time, we can take advantage of, multiplying n by a constant. And that's what we're going to need actually in letter A. 1, 3, 5, 7. So I'm going to think of the term numbers and how we can use that to get each answer. We need to come up with an equation sort of that matches this. So first I'm just going to write out what is the pattern that I see. And pretty easy to tell. This is just a series of odd numbers. The pattern is that the terms increase by 2. And so to make things increase by 2, what we learned in the previous question is that we can multiply n by 2, right? 2 times 1, 2 times 2, 2 times 3. Every time it increases by 2. So if we do that in this question, and we start with a 2n, we do 2 times 1 and we would get 2. 2 times 2 would be 4. 3 times 2 would be 6. And you can see we're a little off still because we didn't start with 2. So we're going to have to do is subtract 1 from the answer in order to start in the right place, and that'll readjust all the rest of the terms, right? So let's check it with the fourth term. 2 times 4 is 8, minus 1 is 7. And that's going to work forever, right? Because we double n and then subtract 1 to get the odd number. All right, let's try letter B. So again, we're going to label the n's. And we're going to have to try to look for a pattern. So the first thing I notice is that these terms alternate in sign. So that's something that we can figure out how to do using a -1. But what else? How do we get from 2 to 5 to 10 to 17? So we're adding 3, adding 5, adding 7. Okay, so that is a pattern, but there is an easier way to spot this. So what else? The other thing I notice here, after kind of a lot of experience with sequences, is that if I square n, we're really close to the answers. 1 squared is 1. I'm 1 away from 2. 2 squared is 4. Add 1 and we get to 5. 3 squared is 9. Add 1 and we get to 10. 4 squared is 16. Add 1 and we get to 17. That's what we want to notice here, okay? So I'm going to also notice that the terms are 1 more than n squared. So we're going to have to combine both of these patterns to make our general term a sub n. So a sub n is going to be some version of -1 to the n. Remember in our previous question, -1 to the n made the signs alternate. So let's check that. We have a -1 to the n. And we want it to go positive, negative, positive, negative. So right now I have -1 to the first, unfortunately, would be negative, but we want our first term to be positive. So the easiest way to do that is just to say n plus 1. So now the first n that I plug in, which is 1, 1 plus 1 is 2, and now this became even. So I just kind of like switched the signs. Let's think that through. If I plug in 1 for n, I'm going to get -1 squared. -1 times -1 is +1. The first term becomes positive. If I plug in 2 for n, 2 plus 1 is 3. -1 cubed is going to be negative, so it stays negative. Plug in 3 for n. This becomes a 4. It's even. This becomes positive. All right, so you can see I took the odd, even. Sorry. I took the negative, positive, and swapped it just by doing a +1 down here. And we also need to make our term itself 1 more than n squared. So I'm going to multiply either a +1 or a -1 by n squared plus 1. So that combined is going to give us each of these terms. All right, let's keep going. Example 4, the Fibonacci sequence, a recursive sequence. Some sequences are defined recursively, meaning the terms of the sequence are defined using previous terms. So the Fibonacci sequence is defined recursively as follows. Instead of just having n in the definition or the equation for each term, we might actually have the previous terms. So here's the Fibonacci sequence. A sub 0, actually, this is interesting as well. This sequence starts out with a 0 term instead of with the first term like we've been doing regularly. We can kind of just assume that everything's going to start at 1 unless we're told otherwise. Like you can see already down in example 5, it says beginning with n equals 0. So this one starts at 0. The 0 term is 1, the 1 term is 1, and then we have this definition in terms of k. A sub k equals a sub k minus 2 plus a sub k minus 1, where k is greater than or equal to 2. Find the first 6 terms of this sequence. That's going to include the 0 term. So the first 6 terms are going to be n's going from 0 through 5. So I'm going to write that out first. All right, and the a sub 0 and the a sub 1 term were already given. They're 1 and 1. A sub 2, if we follow this pattern, 2 is k. So 2 minus 2 means this would be a sub 0. 2 minus 1 means this would be a sub 1. So if we piece that together, the second term, or the n equals 2 term, is a sub 0 plus a sub 1. So that's 1 plus 1. So we get 2. A sub 3, if we follow this pattern, it's going to be a sub 1 plus a sub 2, which is 1 plus 2, which is 3. A sub 4 would be 2 plus 3, or a sub 2 plus a sub 3. So it's 5. And a sub 5 is going to be a sub 3 plus a sub 4, so 3 plus 5. So we get, oops, that should be equals 8. Okay, so recursively defined sequences are a little trickier. In order to get like a sub 10, for example, we'd have to find all of the previous terms before we can get to 10 so that we know the previous terms to plug in. But to say this in just common language instead of this kind of bizarre looking definition, the Fibonacci sequence starts with 2 1s, and then every term after that is the previous 2 terms added together. So we do 1, 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, etc. That's how the Fibonacci sequence works. All right, that brings us to example 5, writing the terms of a sequence involving factorials. So we're going to go back to the beginning for just a second to look at the definitions. We have our second official definition here, factorial. If you've taken statistics, you've probably seen this. If not, it's a factorial, something you might remember from a middle school math course, but most of our high school math courses don't involve factorials. The idea isn't too hard though. If n is a positive integer, n factorial is defined as n factorial equals 1 times 2 times 3 times 4 times dot 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 times n minus 1 times n. As a special case, 0 factorial is defined as 1. So, I mean, just to kind of make this clear, let's do a couple examples over here on the right. So we have 0 factorial, 1 factorial, 2 factorial. Let's do like the first 4. Sorry, the first 5. 0 factorial is defined especially as 1. A 1 factorial would be also just 1. 2 factorial would mean 2 times 1. 3 factorial would be 3 times 2 times 1. 4 factorial would be 4 times 3 times 2 times 1. Okay, so you get the idea, hopefully. Any positive integer or positive whole number, n, factorial, you just multiply all the digits from that number down to 1. If the number is referred to as n, we usually list it out like it says on here. We would do, I mean, if I'm following the pattern here, I was writing the numbers down. So it'd be n times n minus 1 times n minus 2, etc., all the way down to 1. And that's kind of as good as we can get with this, but just think about if we're starting with some n, the next term is obviously going to be n, like 1 lower than n, and then 2 lower than n, etc. That's going to come into play when we think about canceling some terms out at some point. But let's look at example 5. All right, we're going to write the first 5 terms of the sequence given by a sub n equals 2 to the n over n factorial, beginning with n equals 0. So if we're doing the first 5 terms and we start with n equals 0, we're only going to go from 0 through 4. So let me write that out first. So we have 0, 1, 2, 3, 4. Okay. And the first thing I'm going to do is just plug in the n's for each n in that fraction. So we have 2 to the 0 over 0 factorial, 2 to the 1 over 1 factorial, 2 squared over 2 factorial, 2 cubed over 3 factorial, and 2 to the 4th over 4 factorial. All right. Anything to the 0 power is 1, and we already talked about that 0 factorial is also 1. So the first term, a sub 0, is just going to be 1. And I'm just going to follow the pattern. So 2 to the first is 2, 1 factorial is 1, so we get 2. 2 squared is 4, 2 factorial, it means 2 times 1, so we have 4 over 2, which is 2 again. A sub 3, 2 cubed is 8, 3 factorial means 3 times 2 times 1, so we get 8 over 6, which reduces to 4/3. And a sub 4, 2 to the 4th is 16 over 4 times 3 times 2 times 1. So we have 16 over 24, which reduces to 2/3. And there we go. There's the first 5 terms. Okay. Next up, we just have some practice with factorials so that we can kind of get used to the idea that when they're in a fraction, oftentimes the easiest thing to do is to cancel some things out to simplify the fraction. So we're going to evaluate by simplifying the factorials. So instead of just trying to type this into a calculator, let's just think through what this does. Okay, so 8 factorial, if we wrote that entire thing out, which we're only going to do for this one, we would get 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? And now on the bottom, think about, we have 2 factorial times 6 factorial. So we have 2 times 1, and 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. Now this is not a case where we're going to have to distribute the 2 to each of these terms and distribute the 1 to each of these terms. This is all multiplication. If we had addition involved, we might have to do some distributive property, but I do not have to do that when everything is multiplication, right? Remember that. So, but we're still in a fraction and everything's multiplied. So now we can see if anything cancels out. And lucky us, we have 6s, 5s, 4s, 3s, 2s, and 1s that all cancel. So all we're left with is 8 times 7 over really essentially just 2, because 2 times 1 is 2. And 8 times 7 divided by 2 gives us 28. So that worked out. It wasn't too bad in the end. I'm going to show you an alternate way that we can write this. So all the way back from the top, instead of kind of writing out each factorial like this, let's just think this through. If we're starting with 8 factorial over 2 factorial times 6 factorial, I can tell that hidden inside of the 8 factorial is a 6 factorial, right? If I do 8 times 7 times 6 times 5, take a look at what's up here. 6 through 1 is 6 factorial. So what I'm going to do is I'm going to pull out the 8 and the 7. So I'm going to say that this numerator is equal to 8 times 7 times 6 factorial. That's the same thing as 8 factorial, right? 8 times 7 times, and then the rest became 6 factorial. On the bottom, I'm just going to leave it the way it is because now the 6 factorials can just cancel. And that's essentially what we did, but it's a little nicer to write it this way. So now we just have 8 times 7 over 2 times 1, which is our 28 again. So let's try doing B and C from that perspective in that way. So letter B, let's see, do we have any hidden factorials that can cancel? So if I compare the 6 and the 5, since those are the two larger numbers, yeah, I should be able to get a 5 factorial hidden from inside of a 6 factorial. And actually, same thing is true for the 2 and the 3. So I'm going to write 2 factorial times 6 times 5 factorial. So that's breaking down that 6 factorial into two terms. And on the bottom, I'm trying to get that 3 factorial to look like a 2 factorial. So I'm going to change it to 3 times 2 factorial times 5 factorial. So if the number was the smaller of the two, I just rewrite it like normal. If the number was the larger of the two, I'm breaking it down to find the smaller one inside of it. But now I found a secret 2 factorial and a secret 5 factorial. So all I have left is 6 over 3. So I suppose my answer is just 2. And yeah, that's correct. Okay, and then in letter C, so now we've kind of gone a little crazy. We only have n, so we don't know what n is, but just like in all of our sequences, n is a positive integer. It's a positive whole number. So like I was showing you a couple minutes ago, n factorial, I showed you could be broken down into n times n minus 1 times n minus 2 down all the way to 1. We just don't know how many terms it is because we don't know what n is. But the second term in n factorial is n minus 1. And if I just write it as n minus 1 factorial times n, that's equivalent to n factorial, right? Think about it. That's the same thing I did with this 6 factorial. I did 6 times 5 factorial is equal to 6 factorial. And so n factorial being equal to n times n minus 1 factorial is the same idea. It's just more generalized. But that's really great because then on the bottom, I can just leave what was already there, the n minus 1 factorial. And now the n minus 1 factorials can cancel. And so I get my final answer is just n. Hopefully that makes sense. Please let me know if you have any questions on that. All right, well, let's keep going. Example 7, summation notation for a sum. All right, so now we're going to look at sigma notation. We've got a new Greek letter here, sigma, and it's a summation symbol in this context in math. So take a look back at the front page. We've got summation. The sum of the first n terms of a sequence is represented by summation is what we call this. We say summation from I equals 1 to n of some general term a sub I, and then we would list out the terms added together. All right. I think the easiest way to do this is just to apply it. So let's try example 7. First one is a summation from 1 to 5 of 3i. So what that means is we're going to find all of the terms from I equals 1 to I equals 5 and add them all together. That's what this notation means to do. So we have 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5. And so you can tell we went from I equals 1 all the way to I equals 5. I plugged in the I every time. And the plus symbols are here, so we're adding all of those together. And that's really all this notation means. We take all of the terms that it's accounting for and add them together. So this takes what we called a sequence and turns it into a series. A series is when we add the terms of a sequence together. And that's what this is. So let's finish this one off. So we have 3 plus 6 plus 9 plus 12 plus 15, and that's going to equal 45 once we add those together. Okay, and that brings us to letter B, where we're going to go from k equals 3 to 6. While I'm thinking about this, it doesn't matter what letter we have here. It could be an I, it can be a K, it can be an N. All it matters is that that same letter appears, same variable appears in our general term for our sequence. and we can plug in each corresponding value for that letter. You also might notice that on the front page, the summation notation had the I equals 1 and the N on the top and the bottom of the sigma. And now in these questions, it's to the side. It means the same thing. Microsoft Word, if the symbol is like in line, it thinks it would be too big to put it underneath and above, so it puts it to the side. If you're going to write this out by hand, what I recommend, that the common way of doing it would be to write it like this. You'd put the symbol, and then you'd put K equals 3 to 6, like on the bottom and on the top, like that. So that's how we're going to typically write this. Microsoft Word just likes to squish everything together. So that's what's going on here. But anyway, so I'll just rewrite it. And that's going to equal, so we're going to plug in the numbers from 3 through 6. So we're going to plug in 3, 4, 5, and 6. So we have 1 plus 3 squared, plus 1 plus 4 squared, plus 1 plus 5 squared, plus 1 plus 6 squared. Okay, and that's what we're going to be adding together. So we'll end up with 10 plus 17 plus 26 plus 37. And we add those all together, we're going to end up with 90. Let's check out this last one here. The summation from I equals 0 to 8 of 1 over I factorial. So this time we get 1 over 0 factorial plus 1 over 1 factorial, etc., all the way through 8. Okay, so if you calculate all these out, you're going to end up with 1 plus 1 plus 1 half plus 1 sixth plus 1 24th plus 1 over 120 plus 1 over 720 plus 1 over 5,040 plus 1 over what, 40,320. If you add all those together, it's going to be approximately 2.71828. Which actually is eerily close to an approximation for the number E. This is kind of where E comes from, but we're not really going to dig into that, but I did think it was interesting. So that's the number E in disguise. And if we kept going and made this upper bound instead of 8, made it really, really big, it would be a better and better approximation for E. But we're not really going to dig into that. Okay, so let's look at example 8 here. But before we look at this, I just want to kind of finish off the vocab from the front. So we've now looked at what a sequence is, what a factorial is, what a summation is. So there are a few more things that we want to look at. First is the properties of sums. This isn't something that's directly going to come into play within this lesson, but let's just take a look at some of these properties. So if C is a constant, just like any number, then if we are doing some sort of summation from 1 to n, and the only thing in our term is C, then the answer would be C times n, because we're just adding C together n times, right? If n is 5, the terms would, and this, let's say that C is, I don't know, 3, then we would be adding 3 together 5 times. So it would be 3 plus 3 plus 3 plus 3 plus 3. The simpler way to write that would just be to do C times n. So that's one property. If we have C times any sort of, function notation of our term or expression that represents a term of the sequence, and C is a constant multiplied by that term, you can pull the C in front, find the sum of the A sub i's, and then multiply the sum by C, and you get the same answer. So we can pull a constant in front of the summation. That's kind of what we can say about that. If we have two things added together within a summation, you can find it as two separate summations and then add those sums together. And the same thing is true for subtraction. We have two more things here. A partial sum. The sum of the first n terms of a sequence is called a finite series, or the nth partial sum of the sequence. N is denoted like this. Notice that the upper bound of our summation is just an n, and the sum stops at a sub n. That's called a partial sum. Whereas we can also have an infinite sum or an infinite series. The sum of all the terms of an infinite sequence is called an infinite series and is denoted like this. And this is kind of a weird concept, but we can actually add infinite numbers together. And you can see here the upper bound is infinity, so that's the difference. Sometimes this sum is even, a finite number. We can add infinite numbers together and get a finite number. But we'll see more about that as we go. So let's take a look at the next example, example 8. Finding the sum of a series. For the series from I equals 1 to infinity of 3 over 10 to the I, find the third partial sum and the sum of the infinite series. So the third partial sum means that we're going to be going from I equals 1 to 3. The terms are still 3 over 10 to the I. And so what we do is we, plug 1, 2, and 3 in for I and add the answers together. And that's going to give us 3 over 10 plus 3 over 100 plus 3 over 1,000. Which in this context is actually going to be easier to grasp, I think, if we write it as decimals. So it's going to be 0.3 plus 0.03 plus 0.003. So if you add all those together, you're going to end up with 0.333. So that's the third partial sum, is what we call that. And then what this question wants us to do is to predict the sum of the infinite series based off of this partial sum. So let's just say that we kept the upper bound as infinity. So we go from I equals 1 to infinity, 3 over 10 to the I. And we want to think about what's going to happen if this pattern continues. Well, we already know the first couple terms are 0.3, 0.03, 0.003. We can already see the pattern, right? It's just going to be 0.0003, 0.00003, etc. And what's going to happen? So we're going to end up with 0.33333 dot 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 when we add those together. And what is that sum? Well, as a fraction, that is the same thing as 1/3. So we can actually add infinite fractions together that follow this pattern and end up with a finite answer, 1/3. We're going to study that a lot more throughout this unit. But for now, let's try 2 more examples, and they're going to be applications of these concepts. Example 9 is compound interest. A deposit of $5,000 is made in an account that earns 3% interest compounded quarterly. The balance is the account after n, that should say the balance in the account after n quarters is given by a sub n equals 5,000 times 1 plus 0.0304 to the nth power. N starts at 0, you can see here. Right, the first 3 terms of this sequence. So that's going to be defined with a capital A this time. Capital A sub 0, sub 1, and sub 2. So all we have to do here is plug in 0, 1, and 2 for n. So I'm going to write that out and then solve. Okay, and this should look familiar. It's a compound interest formula from back towards the beginning of the school year, but now it's defined using a sequence. But let's just plug each of these in. If you raise anything to the 0 power, you get 1. So the first term is just going to be 5,000, and this is a dollar amount, so now I'm going to include the dollar sign for the answer. For the second one, we're raising that parentheses to the first power. I've already typed this into my calculator, and I get $5,037.50. And for the third one, I'm going to get $5,075.28. And you can see that it's after n quarters. So this is going to be after 1 quarter and after 2 quarters. We're making 75 bucks total after 2 quarters. Not bad. Letter B, find the balance in the account after 10 years by computing the 40th term of the sequence. First, let's think about why would that be the 40th term? Well, n is the number of quarters that have gone by. A quarter is, a quarter of a year. That's what that means. So after 10 years, there's going to be 40 quarters, 40 quarter years, because there's 4 in every year. Makes sense. So we have a sub 40. I'm going to plug in 40 for n. And I'm going to get $6,741.74. So after 10 years, we made 1,700 bucks off of this. Not bad. Okay, let's go to example 10. Population of the United States. For the years 1980 through 2007, the resident population of the United States can be approximated by this model, where A sub n is the population in millions, and n represents the year, with n equals 0 corresponding to 1980. Find the last 5 terms of this finite sequence. It's finite because the n stops at 27. And this represents the US population for the years 2003 through 2007. Okay, we can definitely do that. So it's going to be 23 through 27 are the last 5 terms. So I'm going to write that out on the left. And I'm going to write out each sequence term with the n's plugged in. This might take me a second, so feel free to do this on your own while I'm doing it. Okay, so I'm going to get 290.2, 293.5, 296.7, 300.0, and 303.4. Each of those represent the population in millions, so I could write million after each one, potentially to show that that is million people in the US. All right, so it follows that pattern. This model says it stops when n is 27, so we couldn't potentially use this to predict how many people are in the US today, but this in no way says that that would be accurate. It's only accurate through 2007. Okay, so there you go. That's the last question. So hopefully now you have some knowledge about sequences and series. Something important to take away from this lesson is the difference between a sequence and a series. A sequence just means, the terms, and a series means the sum. That's it. Thanks for watching. Have a great day.